Welcome to this explainer. Listen, if you're currently studying physics, you already know the deal. Electromagnetism can feel a lot like hitting a massive, calculus-heavy brick wall. But seriously, don't panic. Today, we're going to completely master the Biot-Savart Law. You can consider this explainer your literal survival guide for that next physics exam. We're going to take all that intimidating complex math and break it down into a highly structured, totally repeatable process. By the end of this, you'll be ready to tackle pretty much any problem they throw your way.
To conquer these intimidating problems, here's our game plan. First, the magnetic field mystery. Second, the Biot-Savart Law itself. Third, our 5 steps to solve problems. Fourth, applying the strategy. And finally, number 5, the Ampere's law shortcut.
All right, kicking things off with Section 1, the magnetic field mystery.
Okay, let's dive into this. For a long time, electricity and magnetism were honestly thought of as completely separate things. But the big, grand mystery of modern physics is figuring out exactly how moving electrical charges actually create magnetic fields. I mean, have you ever wondered how information is stored so reliably on your computer? Well, the external hard drive you use every day works precisely by magnetically encoding that information. This device, and frankly, almost all the tech running our modern society, phones, TVs, the internet, relies completely on our ability to produce and control magnetic fields using electric currents. So this connection between electricity and magnetism, it isn't just some abstract theory, it is quite literally the engine of the digital age.
Moving right along to Section 2, the Biot-Savart Law.
So if moving charges create magnetic fields, we obviously need a mathematical master key to calculate exactly what those fields look like, right? And that's true no matter how weird the shape of the wire carrying the current is. Conceptually speaking, the Biot-Savart Law is exactly that master key. It's named after 2 scientists who spent their time investigating the interaction between straight wires and permanent magnets. And this empirical law is the exact equation we use to calculate the precise magnitude and direction of a magnetic field produced by an arbitrary distribution of electric current. Basically, it tells us how one tiny, microscopic piece of current contributes to the overall magnetic field at any given point in space.
Now, what's really interesting about this slide is how we can visually break down the anatomy of this equation. Imagine a straight wire carrying a current, which we'll call I. We want to focus on just one microscopic infinitesimal wire segment. We call that DL, which points in the exact same direction as the current. Now, to find the magnetic field at a specific spot, let's call it point P, we measure the distance r from our little segment all the way to P. We also draw a unit vector, r hat, pointing straight from the segment to P. And finally, the angle between our current segment dl and our unit vector r hat is our angle, theta. These right here are the essential puzzle pieces you're going to need for every single calculation. Okay, so to lock this into your memory for exam day, remember these absolute key components. The formula starts with a constant called the permeability of free space. Then it includes your current, your tiny segment length, and your distance squared. But listen, the most absolutely vital part of the whole equation is the vector cross product of the current segment and the unit vector. Why? Because the magnetic field that gets produced has absolutely 0 component running parallel to the current element itself. The field is entirely perpendicular, so calculating that cross product is absolutely essential to finding the field's true direction. Which brings us perfectly to Section 3, the 5 steps to solve problems. All right, if you are a focused learner wanting to totally ace your test, grab a pen because this is the moment to take notes. Integrating vector cross products can get super messy. But if you memorize this exact framework, you can solve any Biot-Savart problem systematically. No panic required. Here is your foolproof 5-step problem-solving strategy. Step 1, identify if you actually need the Biot-Savart method, or if you can look for symmetry to use a shortcut we'll talk about in a minute. Step 2, physically draw the current element length and a unit vector right there on your test paper. I'm serious, visualizing the angle is half the battle. Step 3, calculate that cross product to get the direction of the magnetic field. Step 4, substitute your given quantities and integrate. And here is a massive pro tip. Factor all the variables that remain constant out of the integral. It makes the math significantly less nasty. And finally, Step 5, verify the direction of your answer using the right-hand rule. Let's actually practice that final step right now together. Literally, hold up your right hand. If you point your thumb in the direction of the current running through a straight wire, your fingers will naturally wrap around that wire in the exact direction of the circular magnetic field lines. Try it. And this brilliantly illustrates the real-world physics happening here.
because when iron filings are sprinkled around a wire carrying a heavy current, they perfectly, magically align tangent to these invisible circular fields. It literally proves our right-hand rule, both mathematically and physically.
Let's move on to Section 4, applying the strategy. So let's shift gears a bit and see how our 5-step framework actually applies to the classic geometrical shapes you are absolutely guaranteed to see on an exam. First up, the infinitely long, thin, straight wire. Following our strategy, we draw our vectors and set up the integral. Now, because the wire is symmetrical about the origin point O, we can use a really clever mathematical trick. We just set the limits of integration from 0 to infinity and then simply double the answer. Evaluating this integral proves that the magnetic field decreases with distance from the wire, and as we just saw, the field lines form those perfect concentric circles right around it. Next, consider a circular arc of wire, and let's say we want to find the magnetic field at the exact center point P. Well, get ready for some major mathematical relief. Because it's a circle, the radial direction and the path along the wire are always perfectly perpendicular. The angle is exactly 90 degrees, and you know what that means? It means that nasty vector cross product from step 3 just turns into simple, basic multiplication. We just pull the current and radius straight out of the integral and integrate over the angle. It's a lifesaver. Now, if we take that arc and extend it into a full closed loop, the magnetic field lines take on a seriously fascinating shape. Notice how the lines behave here. When you're really close to the actual wire, the lines are almost perfectly circular, just like the straight wire we looked at earlier. But as you move toward the center of the loop, the fields combine, and one specific, perfectly straight field line shoots right through the central axis of the loop. And finally, Section 5, the Ampere's Law shortcut.
Okay, if just the thought of evaluating those complex Biot-Savart integrals had you stressing out, take a deep breath. Physics actually provides us with a really powerful shortcut for the stressed student, but only when the conditions are just right. We call it Ampere's Law. So the crucial point is knowing when to use which tool, which, if you recall, relates right back to step 1 of our study guide. The Biot-Savart Law is universal. It works for any arbitrary, weirdly shaped distribution of current, but it usually requires complex integration. Ampere's Law, however, is a relationship based on the line integral of the magnetic field. When a problem features high symmetry, like an infinitely long straight wire or a perfectly cylindrical current, Ampere's Law allows you to factor the magnetic field entirely out of the integration, and that results in incredibly simpler math.
Now, unlike electrostatic fields, static magnetic fields are not conservative. That means the line integral between 2 points depends entirely on the specific path you choose. Ampere's law relates the field's line integral around a closed path, which we call an Ampere loop, directly to the total electric current enclosed inside that path. Basically, if you draw a path that encloses the wire, the integral equals the permeability constant times the current. If you draw a path that doesn't enclose the current, the line integral is just 0. It's that simple.
Let's move to and see how this builds into the real world. When drawing arbitrary Ampere paths around multiple wires, you only calculate the net enclosed current. So think about it. If one wire carries 5 amps up and another carries 5 amps down, the net current enclosed by a loop around both of them is 0. That means no external magnetic field is present. And actually, this is exactly why the wires in your everyday electrical cords are bundled so tightly together. The current flowing towards your device and away from your device perfectly cancel each other out, which prevents stray magnetic fields from messing with your environment. Pretty cool, right?
So there you have it. By mastering our 5 steps, from checking for symmetry in step 1 to setting up that Biot-Savart cross product, pulling out your constants, and verifying with the right-hand rule, you are now fully equipped to break down any electromagnetism problem on your exam. We've seen firsthand how massive things like power wires and everyday hard drives rely on these exact macroscopic equations. But I want to leave you with this final provocative thought. As our technological devices continue to shrink down to microscopic, even quantum levels, will these classical macroscopic laws of magnetic fields still hold up? Or is there an entirely new physics out there just waiting to be discovered? Keep studying, keep asking those big questions, and hey, you just might be the one to find out.